Hi, today I'm teaching ES Level Further Maths under the Edexcel specification. I'm on the core module and today I'm doing chapter 2, which is Argand diagrams. So you can represent complex numbers on Argand diagrams where the x-axis is the real axis and the y-axis is the imaginary axis. So the complex number z equal x plus iy can be represented on the diagram by the point P, xy, where x and y are Cartesian coordinates. So you see there's a diagram where z equals 2 plus 2i, and you see the point. And then I've also done one at z equals 2 minus i. Complex numbers can also be represented as vectors. So the complex number z equals x plus iy can be represented as a vector xy on Argand diagrams, and these vectors can then be added or subtracted. So for example, here you see on the diagram we have z1, where z1 is 2 plus i, and we have z2, where it is 1 plus 2i. And we can do z1 plus z2, and that makes 3 as a vector, and you can represent that on the diagram. So now I'm going to be talking about modulus and argument. So the modulus of a complex number, which is z in between those lines, is the distance from the origin to that number on an Argand diagram. For a complex number, z equals x plus iy, the modulus is given by z in those lines is equal to the root of x squared plus y squared. And it can be written as z in the lines, r, or x plus iy in the lines. The argument of a complex number, argz, is the angle between the positive real axis and the line joining that number to the origin on an Argand diagram. For a complex number, z equals x plus iy, the argument, theta, satisfies tan theta is equal to y over x. The argument is usually given in the range minus pi is less than theta, greater than or equal to pi, and this is sometimes referred to as the principal argument. So because this is measured in radians, we know that pi is 180 degrees. And so when we're measuring it on an Argand diagram, you know, like a circle where we have pi, which is 180 degrees, and that's the top bit, and then minus 180 degrees, which is the bottom bit. And I'll show this more in a diagram soon, but I just want you to understand how this works. Okay, so now I have a practice question where we have the complex number 2 plus 7i, and we need to find the modulus of z and the argument of z. So first I'm going to draw it on a diagram. This is going to be really bad because I'm doing this freehand, but whatever. That's fine. And this is 0. So we know that's 2 on the x-axis, so like 2, and then 7. So that's 2 plus 7i, and we want the modulus of z. So I'm going to do 7. 2, 7. So this is like a triangle, and then you know we do the root of x squared plus y squared, so that's 2 squared plus 7 squared, which is equal to root 53. You can just put that in a calculator. And I want to do the argument of z, so that is tan theta. So we're finding the angle here because it's the angle from the positive real axis, so the x-axis on the right side of the diagram. So we want this angle here. So that is tan theta is equal to y over x. So 7 over 2. So when you put this in a calculator, you do tan to minus 1, 7 over 2. And you get an answer in radians. You should set your calculator to radians when you're doing Argand diagrams. So you come out with the arg of z is equal to 1.29 radians. That's to 2 decimal places, but you get the idea. Okay, so this looks kind of odd, but bear with me. So I want to let alpha be the positive acute angle made with the real axis by the line joining the origin and z. And so I've split this graph up into 4 quadrants. So we have the top right one, the top left one, the bottom left one, and the bottom right one. So in the top right, argz is just equal to alpha because that's the angle made with the positive x-axis. In the top left one, we have pi minus alpha because pi is 180 degrees, so that's the whole upper half, minus alpha because you're taking away the angle you found because you want the angle that's made with the positive x-axis, so the x-axis on the right. In the bottom left, you have minus pi plus alpha, which for the same reasons as the top left, you want the angle with the positive x-axis, So you take away what you found because you're at minus 180. And then you have the rest of the angle. And in the bottom right, you have argz is equal to minus alpha because that's the angle made with the positive x-axis. Okay, so I've got an example question here where z is equal to minus 4 minus I. And we want to find the modulus of z and the argument of z to two decimal places. So I'm going to start off by drawing a diagram, granted not very well because I don't have a ruler or anything. So minus 4, I'm going to put minus 4 there, and so we have minus 1, minus 4, going to be there. And so we want to find the modulus of z, so I'm going to draw a little triangle. With that being minus 1, being minus 4. And then we want to do the root of minus 4 squared plus minus 1 squared, and that is equal to the root of 17. And that is the modulus of z. And I want to find the argument of z. So we can find that angle there. So we do tan the minus 1 of y over x. So minus 1 over minus 4, which makes 1 over 4. And that is equal to 0.2449 radians. Well, there's a ... because it goes on. And then, because we want the angle from the positive x-axis, we do Rz is equal to pi plus, or minus pi plus 0.2449, and that is equal to minus 2.90 radians to two decimal places. Okay, so now moving on to modulus argument form, and this is for any complex number z with modulus z is equal to r and argument of z is equal to theta. The modulus argument form of z is r brackets cos theta plus I sine theta. Okay, so now I have an example where z is equal to minus root 3 plus I, and I want to put it in modulus argument form. So first I'm going to draw a diagram. Oh god. And so we have minus root 3. That's there. Then we have 1. So it's about there. And I want to find the modulus first, so I'm going to do root 3 squared plus the root of 1 squared, which is equal to the root of 4, which is equal to 2. So r is equal to 2. And then we want to find the argument. So we have this angle here. And so we do tan the minus 1 of y over x. So 1 over root 3. So we have to times everything by root 3. So that is tan to the minus 1 of root 3 over 3, because we don't want the sides on the bottom, because it's not rational. And that makes pi over 6. And so now we have pi minus pi over 6, because we want the angle with the positive x-axis, and right now we have this angle. And that is equal to 5 pi over 6. And so now we need to write this in modulus argument form. So we have RR, which is 2 brackets cos theta, so theta is 5 pi over 6, plus I sine 5 pi over 6. And that is how you write something in modulus argument form. Okay, so now I want to talk about some quick rules that you should remember. So for any two complex numbers z1 and z2, the modulus of z1 and z2 is equal to the modulus of z1 times the modulus of z2. The argument of z1 and z2 is equal to the argument of z1 plus the argument of z2. The modulus of z1 over the modulus of z2 is equal to the modulus of z1 divided by the modulus of z2, and the argument of z1 over z2 is equal to the argument of z1 minus the argument of z2. Okay, so now I'm doing an example where we have z1 is equal to 2 cos pi over 15 plus I sine pi over 15, and z2 is equal to 3 cos 2 pi over 5 minus I sine 2 pi over 5. So the first thing I want to point out is that we have a minus I sign, which means that we have to turn this into modulus argument form because it's not already, despite looking very similar. So z2 is actually 3 cos minus 2 pi over 5, because cos minus theta is equal to cos theta, plus I sine minus 2 pi over 5, and then for sine minus theta is equal to minus sine theta. So now we want to find z1, z2, just to show you how to do it. So we have on z1 r equal 2, and on z2 r equal 3. So 2 times 3, that's equal to 6. What else do I want? Arg z1, z2. That's the argument of z1 plus the argument of z2. So pi over 15 plus 6 pi over 15, well, minus 6 pi over 15, because we have minus 2 pi over 5, is equal to minus 5 pi over 15. You can then put this into z1, z2 modulus argument form. So we have 6 cos minus 5 pi over 15 plus I sine minus 5 pi over 15. And then finally, you can turn this into the form x plus iy by putting it in the calculator. So when you put this form into the calculator, it will give you in the form x plus iy. And so when you do that, you get the answer 3 minus 3 root 3 I. And that is it in the form x plus iy. Okay, so now I want to talk about loci on an Argand diagram. So for two complex numbers, z1 equals to x plus iy, and z2 is equal to x2 plus iy2, the magnitude of z2 minus z1 represents the distance between the point z1 and z2 on an Argand diagram. And so where loci comes in is we can take this idea and apply it to a circle, where given z1 is equal to x1 plus iy1, the locus of point z, where z is like an invariable point, on an Argand diagram such that the magnitude of z minus z1 is equal to r, or the magnitude of z minus x1 plus iy1 is equal to r, is a circle with centre x1, y1, and radius r. So that means that we have the centre of the circle, z1, and any point on the circumference of that circle, because that's the distance from the centre to the circumference is r, is one point that is given. So it's the locus of points is anywhere on this circumference. Okay, so now I'm going to do an example question. So in this example, we have z satisfies that the magnitude of z minus 4 is equal to 5. And so we know typically it's z minus brackets x1 plus iy1 is equal to r, and where r is the radius of the circle. And we see we have no I, so that means there's no y equals 0. So we have the circle with centre 4, 0, because we only have the x value. And we know that the radius is 5. So now we can sketch this. So I'm going to do a really rough one just to explain. So 4, that's fine. And then that isn't even a circle, but whatever. And we know that any distance from the center of the circle is 5. Do a better one when you do it in your exam, but I'm doing this on a laptop, so not very easy. And then the next part of the question is that and so it satisfies that bit, but it also satisfies that the imaginary of z is equal to 0. Oh yeah, label your axes as well. And so when the imaginary, or the y-axis, is equal to 0, we have these 2 points that cut into the x-axis, so we know that it's always equidistant from the circle as well. So it's 4 minus 5, so we have the point -1, 0, and we have the point 9, 0. So this means that z is equal to -1, or z is equal to 9. Because they want us to give our answers as complex numbers, not coordinates. And then the next part of the question is the real axis is equal to 0. And this is a little bit harder because I want to turn our equation into Cartesian coordinates. So we have, so you know the equation for a circle is x minus the number plus y minus the number is equal to r squared. So x minus 4 squared, oh yeah, I forgot to square the, but whatever, plus y squared is equal to 25, because 5 squared is 25. So we have x squared minus 8x plus 16 plus y squared is equal to 25. And we know that the real axis is equal to 0, and the real axis is x. So x equals 0, so we can get rid of these two. So we just have y squared plus 16 is equal to 25. And so we can take away the 16, so y squared is equal to 9, and y equals to plus or minus 3. So then z equals to 3i, or z equals to minus 3i, because when we're doing y, it's always iy, so there's always the I involved. Okay, so now I have an example where the magnitude of z minus 5 minus 3i is equal to 3. So we know that the circle has a center 5, 3, and a radius of 3. So I'm going to sketch that really quick. 3, 5. And you want to be sort of aware of where you're sketching. So for example, I know that the radius is 3, so I know that it's going to touch the x-axis in one place, and it's not going to touch the y-axis because we are on 5 on the x-axis, and the radius only goes 3 to the left, so the furthest we're going to get is 2. So just when you're sketching, you want to be aware of where the circle is on the graph. So then we want to find the Cartesian equation of this locus, so we have to do the equation of squares. So we have x minus 5 squared plus y minus 3 squared is equal to 9, because it's a little off screen, is it? There we go. And then we want to find the maximum value of argz in the interval minus pi to pi. And so this sounds really daunting, but what you do is you basically make 2 triangles that are both like tangents to the circle. So we have one on the x-axis, and we have one coming from the origin up and being a tangent. But this is just one triangle, it's kind of hard to work with. So then what I do is I do one to the center. So then we have 2 triangles that both have right angles. And so I'm just going to focus on this bottom one because it's a lot easier to read. So we have 5, 3. So we're going to do what we did before, where it is tan to the minus 1, and it's y over x. So we have 3 over 5 and then when we get that answer, we want to times that by 2, because there's actually 2 of those angles, one there and one there. And so the answer in total is 1.08 radians to 3 significant figures. Okay, so now we have an example where we have the complex number z equals x plus iy, and it satisfies the magnitude of z minus 12 minus 5i is equal to 3. So we have a circle, and we know the center of that circle is 12, 5. Okay? So now I'm going to sketch this. gonna be sort of bad, but whatever. I am an RE because I remember to leave my yeah, that's right. It's fine. And so that's 12, 5. Okay, and the actual question is asking us to find the minimum and maximum value of the magnitude of z. So that means we want the closest value and the furthest value. So it's actually just going to be a straight line through the circle, touching the center of the circle, but I don't have the steadiest hand, because that's the closest distance and the furthest distance. So we know we have the center of the circle. So first we want to find the distance from the origin to the center of the circle. So the magnitude from the origin to the center, and that is 12 squared plus 5 squared, and that is equal to 13. And then we can plus and minus 3 because 3 is the radius, and we know that there's a distance of minus 3 and a distance of plus 3 here from the center on this line. So one value is 10 and the other value is 16. So z is equal to 10 or z is equal to 16. Okay, so now given that z1 is equal to x1 plus iy1 and z2 is equal to x2 plus iy2, the locus of points z on an Argand diagram such that the magnitude of z minus z1 is equal to the magnitude of z minus z2 is the perpendicular bisector of the line segment joining z1 and z2, which means any point on this perpendicular bisector is an equal distance away from the points z2 and z1. So it's the locus of points that is an equal distance away from z2 and z1, and so that locus is the red line, and it is the perpendicular bisector of the line that joins z1 and z2. Okay, so now I have an example question where the magnitude of z minus 3 is equal to the magnitude of z plus 1. Also, I know I'm zoomed out a lot, but I need quite a bit of space to show all of this, just in case. So we know that there is a line that joins the points 3, 0, and 0, minus 1, because we can get that from the magnitudes we were given. And so let's first draw this on a diagram. I'm going to do it on the left here. Oh god, that's awful. So we have 3, and then minus 1, 3, and then we have like a line that joins them. Obviously this like continues on, but I'm just showing this as an example. And then we're obviously going to get its perpendicular bisector, because we want the loci of points that are equidistant from minus 1 and 3, or like those lines. So first we can work out the gradient of the line from minus 1 to 3. So dy over dx, and we end up having a gradient of 1/3. And we know that the gradient of a perpendicular bisector is the negative reciprocal of this. So we know that that gradient is minus 3, okay? And we also know that this perpendicular bisector passes the midpoint joining 0, minus 1 and 3, 0. So we know that it passes through 3 over 2 minus 1 over 2. Okay, and we can do the equation of a line. So we have y equals, or well, I'll just sub in y instantly. So we have minus 1 over 2 is equal to minus 3 brackets 3 over 2. And then we put this in a calculator and we can find out that the y-intercept then is plus 4. So y equals minus 3x plus 4. And that is the Cartesian equation of this locus. Okay, and now this next part of this question asks us to find the least possible value of the magnitude of z. And this means that from the origin, we want to find the smallest magnitude to a point on this locus. Okay, so I'm just going to take this line here. It's like a rough estimate of the smallest value, and then we can work it out, okay? So we know that from the origin to this locus has the same gradient as the line from -1 to 3. Okay, so that means that this line has one third is the gradient. And because it passes through the origin, the y-intercept is 0. So the equation of this line is just y equals to 1/3 x. Okay? And we have one value of y here and one value of y here. And we know that these two lines will like share a point, and that'll be the point that is the smallest value from the origin to the perpendicular bisector. So we can just sub this in. And so we have -3x plus 4 is equal to 1/3 x. And if you do a bit of substitution, you can find out that x is equal to 6/5 and y is equal to 2/5. And then, if you remember before, for magnitude you do the square root of x squared plus y squared. And so we sub in x and y. And so we sub in, the square root of 6/5 plus the square root of 2/5 squared. And your answer is 2√10/5. So this is another little bit on loci, but given that z1 is equal to x1 plus iy1, the locus of points z on an Argand diagram such that the argument of z minus z1 is equal to theta is a half line from, but not including, the fixed point z1, making an angle theta with a line from the fixed point z parallel to the real axis. Okay, so now I have an example where the argument of z plus 3 plus 2i is equal to 3π/4. So first I want to draw this because we know that it starts from -3, -2. So we know that this is in the bottom left quadrant. Yeah. So draw, put it one further, and then we have -3, -2, and so we have this point here, and it extends some point this way because we know that the angle goes anti-clockwise, and we have 3π/4, which is like a big angle. Yeah, so we know that it extends like upwards to the left. Because it's anti-clockwise from the positive real axis. Anyway, so we've sketched it, and then the next part of the question is to find the Cartesian equation of the locus. And we do this by, first I want to separate the real and imaginary part. So we have arg brackets x plus 3 plus y plus 2 equal to 3π/4, and you can actually take out the argument because the argument is like 10 to the -1. So we have y plus 2 over x plus 3 is equal to tan 3π/4, and that is equal to -1 when you put it in the calculator, which means that we have y plus 2 is equal to -x plus 3. And that means that y is equal to -x minus 5. But because it's a locus, we need a range. And we know that the point starts, x is equal to -3, and it can't be at the original point, so it has to be greater than. So that means that x is greater than -3. Okay, so now I quickly wanted to go over regions. Regions is literally just the same thing with inequalities, so certain parts are shaded in. So I took one of the final questions, and it is, so we have, first of all, the magnitude of z minus 4 minus 2i is greater than or equal to 2. And so this is the equation of a circle. So I'm going to first of all draw that, and it's a circle with center 4, 2. So we're in the upper right region. And it has a radius that is greater than or equal to 2. And then z is z minus 4 is greater than, no, z minus 4 is less than z minus 6, sorry. And so we have 4, we have 5, we have 6, okay. And those two lines, z minus 4 and z minus 6, they are lines that are intersect, and so we have a perpendicular bisector, midpoint of 5, right, because the line meets at 5, and the 4 side is greater, so it's shaded in this side here. And then our final bit, where we have 0 is less than or equal to the argument of z minus 2 minus 2i, which is less than or equal to pi over 4, and pi over 4 is like 45 degrees if we're talking degrees. And so we have this line. I'm gonna fuck, I can't even undo the shading, whatever, fine, I can fix this. And so we have the line 2 minus 2i, so that's 2 2 here. So we have, and it's anti-clockwise from the positive real axis, so we have the angle there. And so it's greater than or equal to, so this bit's shaded, which means quite literally it's within the circle, bounded by this line and this line and this line. And that is what you need to shade in. And that is all you need to know about Argand diagrams. So thanks for watching. Bye bye!